We are given this parametric system of equations shown here in white. X of t equals 5t plus 10, y of t equals negative 5t squared plus 50. And folks, first of all, don't be intimidated by this x of t and y of t. You could just simply rewrite this as x and y respectively. So here we have this parametric system of equations, and this is foreign to us. What we're used to seeing are x's and y's. So we can convert this parametric system of equations to a single rectangular coordinate equation. And the way you do that is you take one of the equations and solve for t, and then you substitute. So I went ahead and took this top equation, x equals 5t plus 10. I solved for t, and I got t equals x over 5 minus 2. And then one could just simply substitute into the equation for y for t. And when you do that and you do the math, you get this rectangular coordinate equation that we're used to seeing. And we're used to dealing with this. We know this is an upside down parabola. And it's going to be relatively wide because this is 1 over 5. So why do we need parametric equations? Why not just convert to something we're used to seeing? Well, here is why. Parametric equations add information about direction and speed. They are great for modeling motion of a particle or object with time. Parametric equations excel at showing where an object is at any given instant, at any given point in time, not just giving its overall path. So these equations in yellow, you could see they contain the element of time. But when we change it to a rectangular coordinate system, we lose time. And when we do that, we lose information. Yes, this equation is going to give us a path, but we're not going to know how fast the particle's traveling along that path with respect to time. We're not going to know where the particle is at t equals 0, or t equals 1, or t equals 2. We don't know which direction it's going. We don't know whether it's going from right to left or from left to right. So that is the reason why parametric equations are so important. And we'll see some examples in a moment. So far, folks, we took this original parametric system of equations and we changed it to a rectangular coordinate equation that we're used to seeing. But it's important to realize that there are an infinite number system of parametric equations that will converge to this same parabolic path. Let me show you what I mean. If we make up a function for x, okay, I went ahead and did that, x equals 10t plus 2, and then we take this x and we plug it into this rectangular equation, we'll get an equation for y. And it turns out that this system of equations right here, x equals 10t plus 2, y equals negative 20t squared plus 32t plus 186 over 5, will also converge to this same rectangular equation. Let's go to Desmos and let's graph this, and we'll show you the difference. I'm going to show you the difference between this parametric system of equations and this parametric system of equations. To be clear, both of these systems, the system circled in blue up top and the system circled in red on the bottom, they're going to have this same path. However, they're going to travel this path differently with respect to time. Let's go to Desmos and take a look at that. Folks, this is how you use Desmos for parametric equations. Here was the original system. X of t equals 5t plus 10, y of t equals negative 5t squared plus 50. It's important for some reason that you use a capital X and a capital Y when you establish your parametric system. The next thing you do is you hit add item and you create a table. That's what I did to get to here. And then you could change that to t, then tab, capital X of t, change that to t, capital X of t, tab, capital Y of t. And then if you enter values for t, let's start with 0, the table will fill in for you. Okay, so I went ahead and did that, and I plugged in t equals 0 all the way through 5, and I got these coordinate points. Okay, then I unhighlighted these, and I went ahead and plotted each of these points with their associated time value. And we got these points here. These points 10, 50, 15, 45 are taken right from the table that we created. Okay, the next thing we see is if we highlight our rectangular coordinate equation right here, we could see that the path fits these parametric equation points. Okay, now what did we do in part 2? In part 2, we found another system of parametric equations that converged to this same rectangular coordinate equation. So let's bring that up. Okay, so here's the second system of equations. Remember, we made this up, x of t. Then I plugged in that for x into the rectangular function, and that revealed a function for y. Then I went ahead and plotted this on Desmos just like I did on the previous graph. Now look at the difference. You could see here's the same original rectangular equation. Look at these. They have the same exact path. But look at the difference. Look where this particle is at time equals 0 versus the original one. The original parametric system at time equals 0 had the particle at the vertex. Here it hasn't reached the vertex yet. So you could see clearly that although it's the same path, you lose information. When you move to a rectangular equation, you lose all of this information in terms of where is the particle located and in what direction is it moving. Look, this one starts at its vertex and then heads downwards. This one starts not at the vertex. It starts here, then it moves up to here at t equals 1 before it comes down. That is the value of parametric equations. They give you more information. They give you information with respect to time. They give you duration. They give you speed. Look at this one. Look how fast it's moving. Here, that distance versus this distance. Okay, this one appears to be moving further in the y direction, further in the x direction than this one. Direction, speed, and movement with respect to time. That's the benefit of a parametric system of equations. We are asked to find the second derivative of these parametric equations, this parametric system of equations. And the second derivative is written like so, d2y over dx to the second power. And folks, we're going to be employing this d/dt operator, if you will. This is saying we're going to take the derivative of what's inside those brackets with respect to t. Okay, recall that to take the first derivative of a parametric equation, we use this formula. We have dy dt over dx dt. The dt's will cancel out, or think about multiplying top and bottom by dt, and you end up with dy dx. So in this first step, we are taking the d/dt operator to y and dividing by dx dt, and that's going to yield dy dx. Now, when we take the second derivative, we do the same thing. We take the d/dt operator, but this time we apply it to dy dx. And again, we divide by dx dt. Let me use a lighter color to do that highlighting. We're going to take the derivative with respect to t of the first derivative dy dx, and again, we're going to divide by dx dt. That is the blueprint on how to do this. So let's proceed with part one. We're going to take dy dx. Again, to do that, we're going to do dy dt over dx dt. So dy dt, we're just going to rewrite e to the 3t, and then we're going to apply the chain rule to the exponent. The derivative of 3t with respect to t is going to be 3, and then we're going to take the natural log of the base, which is e, therefore it's just 1. In terms of dx dt, we're going to do a similar process. We are going to rewrite 3e to the 2t, and then we're going to take the derivative of the exponent, which is 2, and we're going to end up with 3e to the 3t in the numerator, and we're going to have this times 2, and we're going to have 6e to the 2t in the denominator. The 3 and the 6 cancel out, leaving a 2 in the denominator. And if you take this e to 2t and bring it upstairs and change the sign of the exponent, we're going to have e to the 3t minus 2t up top. And when all the smoke clears, the first derivative is going to be e to the 1t over 2. Folks, before we move on, I want to do that dx dt a little cleaner. So let's go ahead and just redo that quickly. To do dx dt, we're going to apply the ddt operator to this function here, 3e to the 2t. So the way to think of this is we're going to do the product rule here. So we have 3 times e to the 2t. Now the way I do this is left d right. So that would be 3 times the derivative of this. And when we take the derivative of this second factor, we're just going to rewrite it as e to the 2t, take the derivative of the exponent, which is 2, and then the natural log of the base, which is just 1. So that's how you do this. You treat this as a product rule. And part 2 of the product rule, of course, is right, which here would be e to the 2t times d left, and the d left is 0. So that was just a cleaner way to take that derivative. I wanted to review that. Let's proceed with part 2, namely taking the second derivative. So here's the original first derivative. Here's dy dx, e to the t over 2. So we're going to take the ddt operator, and we're going to apply it to dy dx. So we're going to take our dy dx and put that within those white brackets, and we're going to take the derivative of this with respect to t, and then we're going to divide by dx dt. We're not going to take any derivative down below. We're just going to take this dx dt that we got, and we're going to put that in the denominator as is. We're not going to do anything to that. All right. Now we're going to take the derivative with respect to t of e to the t over 2, which is 1/2 e to the t, and that's going to stay as is, 1/2 e to the t, because the chain rule, just the derivative of t with respect to t is just 1. So now we're going to have this over 6e to the 2t. We're going to multiply top and bottom by 2, which is essentially placing the 2 in the denominator. And we're going to have 1 over 12 e to the t over e to the 2t, and then we're going to bring this to the bottom, change the sign of the exponent to negative, and we're going to end up here in yellow, written very small, I apologize, 1 over 12 e to the t. And folks, that is your second derivative of this parametric system. Next, we are given the second set of parametric equations, this second system, and we're asked to find the second derivative. And folks, you might see this as x equals t cubed plus t squared, and y equals 7t squared minus 4. But again, don't be intimidated by this x of t and y of t. It's the same as just saying x and y. Okay, so what's our game plan? First, we're going to find dy dx, the first derivative. And how do we do that? We find dy dt and then dx dt. And once we find dx dt, we're not going to change that. We're going to take whatever this is, and we're going to use that in our formula to get the second derivative in part 2. We're going to keep that as is. Okay, so let's go ahead and find dy dt and dx dt. Dy dt is over here. We're just going to do the power rule, so that is going to be 14t. And dx dt, which we're going to keep as is going to be 3t squared plus 2t. Okay, next what we can do is we can pull out a t down below, and we're still trying to find dy dx, so we can simplify this. So 14t on the top, if we pull out t as a GCF, we're going to have 3t plus 2. Okay, all great math students always double check and redistribute when they pull out a GCF. If we do that, we see that we have 3t squared plus 2t, and now these t's cancel out, and our dy dx, our final dy dx, is going to be 14 over 3t plus 2. Okay, for part 2, folks, is we're going to do this. We're going to apply the ddt operator to dy dx, and we're going to keep that dx dt the same. We're not going to use this version where we cancel things out. We're going to take this original version right here. Okay, so let's do that. Let's execute that plan. So we're going to take ddt of dy dx. dy dx is right here in its simplest form, 14 over 3t plus 2. And then we're going to divide that by the original dx dt, 3t squared plus 2t. Okay, let's come back in a few moments and we'll take that derivative together. Okay, folks, here we go. We're going to do part B. Here's part B. Right here, we're going to apply the d dt operator to dy dx. Here's dy dx right here. Okay, so we're going to take the derivative with respect to t of dy dx. And dx dt is going to stay the same. We're not going to do anything to that. Look, dx dt, if we did the power rule here, is 3t squared plus 2t. That's going to stay as is. The only thing we're going to do to that as we move across is maybe pull out the t again for the GCF. Okay, let's take the derivative of what's in the brackets here. Let's change this to 14 times 3t plus 2 to the negative 1. And then let's use the power rule. So in the numerator, we're going to have negative 14 times 3t plus 2 to the negative 2. And then we're going to apply the chain rule by taking the derivative of what's inside the function, and that's going to yield 3. And on the bottom, let's go ahead and pull out the t as the GCF. So we're going to have t times 3t plus 2. And we do that because we know we're going to bring this down to the denominator, and we're going to combine these two factors of 3t plus 2. Okay, so next, folks, we're going to go ahead and, as described, we're going to bring that down to the denominator. We're going to multiply by 14 and 3. We're going to get negative 30 plus 12 is 42. And we're going to have t times 3t plus 2 to the first power times 3t plus 2 to the second power. And that's just from bringing this factor down to the denominator and changing the sign of the exponent. And then when all the smoke clears, we're going to combine these, and we're going to have this to the third power. And folks, that is your second derivative. Again, the emphasis, the thing to remember is once you take dx dt, that stays in part 2. You don't do anything to that. We are told that there is a particle traveling along a parametric curve defined by x of t equals 4 of t, y of t equals negative 2t for t is greater than or equal to 0. The path of the particle lies on A, and it gives us 4 choices. Okay, so when you're looking for the path of the particle, that's a signal that we need to convert this to a rectangular equation. So we start out with x of t equals 4t and y of t equals negative 2t. Okay, so we're probably talking about time here because they say time is greater than or equal to 0. Okay, so again, folks, the theme of this video has been don't be afraid of x of t and y of t. You can just go ahead and consider that x and y. So the way to convert from a parametric system to a rectangular equation is to solve for t and substitute. So let's go ahead and take the top equation and we'll divide both sides by 4 and we'll end up with t equals x over 4, and now we'll substitute that into the y equation and we'll end up with y equals negative 2 times x over 4. Okay, this was t right there, and the 2's will cancel out and you'll end up with y equals negative x over 2, which is just like negative 1/2 x. So that would be a linear equation. So the choice would be choice C. Next, we are told a particle is moving along the y-axis with this velocity 8 minus 2t for t is greater than or equal to 0. The particle moves upward until it reaches the origin, then it moves down. Which of the following could be the position function? So folks, this is a very sneaky problem because that origin is not what we normally think of as that position right there. This is a graph of the y position with time. When we think of the origin, we're thinking of the xy graph where y equals 0 and x equals 0. So when they say reaches the origin, that tells us that the y value is 0, but we don't know what position along the horizontal axis this represents. We don't know what time that is. So to me, this is what's happening with this graph. The particle moves upward, okay? Time is going on until it reaches the origin. That means the y value is 0, and then the particle starts to move down. So not only do we know that the y value is 0, but we also know the velocity is 0. That's what you have when you reach a minimum or a maximum here. You have a velocity equals 0 right there. That's when particles turn around. So we can do two things. Here's the velocity equation. We can take the antiderivative to get the position function, but we don't know what that c value is. So we're going to use this information to determine what that c value is. Okay, so the first thing we do is recognize that the velocity equals 0 at that time t. So we set the velocity equal to 0, we get t equals 4. The other thing we know that at that same position, the y value is 4. The y value is 0. So what we're going to say is that when you plug in 4 for t into the y equation, we're going to get 0. So we're going to set this candidate equation, negative t squared plus 8t plus c equal to 0. And when we solve, we find that the c has to equal negative 16. So therefore, we can plug that back into our original antiderivative and determine that that is our final equation, which is going to be choice A. Next, we are given x of t equals this polynomial, y of t equals this polynomial, where t is element of all real numbers. Find the value of t, what value of t will a tangent to the parametric curve have a slope of 4? So folks, this tells us that we have to find the derivative. We have to find dy dx. Okay, so how do we do that? We find dy dt over dx dt. Right. So let's do that. Dy dt is going to be 2t minus 3. And dx dt is going to be 4t plus 1. And they want to know at what value of t does the derivative equal 4. That is what the slope of the tangent line, it's the derivative. So we'll set this equal to 4, then we'll cross multiply. 2t minus 3 equals 16t plus 4. And we'll have 14t equals negative 7. T equals negative 1/2. Let's see if that's a choice. And it is choice A. Next, we are given this parametric system, x of t equals 2t squared, y of t equals t to the third power, and we're asked to find the second derivative at t equals 3. So folks, we know how to do this. Here's our roadmap. Here's our game plan. To find the second derivative, we're first going to find dy dx, dy dt over dx dt. We're going to keep this dx dt as is. We're not going to do anything to that. And we're going to bring that into the denominator of part 2. In the numerator of part 2, we're going to apply the d dt operator to dy dx. So here we go. We went ahead and did that ahead of time. Here we're getting dy dx. We do dy dt over dx dt. We get 3t over 4 when we simplify. Now we're going to take the derivative of dy dx with respect to t here. This is part 2. We're now getting the second derivative. And we're going to divide by the original dx dt. We didn't do anything to that. All we did is take this dx dt and bring it down to part 2. And when we take the derivative of 3/4 of t, we get 3/4 over 4t. The 4 goes down below, we get 3 over 16t. So they wanted to know this second derivative when t equals 3. So if you take out this t and replace it with a 3, the white 3 on top and the blue 3 on bottom cancel out, and you're left with 1/16, which is choice A. We are told that there's a particle in motion along this curve, r of theta equals 3 cosine of 2 theta, and theta is a function of t such that d theta dt equals 1/3 radian per second when theta is pi over 6. At that point, what is the rate of change of the particle's distance from the origin? So the particle's distance from the origin is your r value. So folks, we can rewrite this as r equals 3 cosine of 2 theta. Okay, let's talk about the intuition of what this graph is going to look like. 3 is going to be the length of each petal, and the fact that there's a 2 here in front of the theta, and that's even, means there are going to be 4 petals. You multiply it by 2 if it's even, and the fact that it's cosine means it's going to be symmetric over the x-axis. So here we have a 4-petal figure that is symmetric over the x-axis. Okay, the first thing to recognize is this part of the equation right here. What is the rate of change of the particle's distance from the origin? So folks, we're looking for dr dt. So since we only have a theta over here, we can go ahead and differentiate this with respect to t on the opposite side. So the derivative of cosine is negative sine, so we're going to have negative 3 sine of 2 theta. Then we're going to do the chain rule, so we're going to have multiplied by 2, and then we're going to have d theta dt. Now, looking at this problem, folks, fortunately, they give us all this information. they give us that d theta dt is 1/3. So let's replace this with 2 times 1/3. And then we're going to have -3 sine of 2 times, and they say when theta equals pi over 6. So 2 times pi over 6, we're going to end up with this. These 3's cancel out. So we're going to have equals -2 sine of pi over 3. Okay, folks, the sine of pi over 3, we call our unit circle. Pi over 3 is just going to be otherwise known as 60 degrees. So pi over 3 is going to be up here somewhere. So that y value will be the sine. This is short. I call that short and long. That's 1/2. And the sine of pi is going to be positive square root of 3 over 2. So we're going to have square root of 3 over 2 replacing sine of pi over 3. Sorry, that's off the screen. And the 2's cancel out, and our final answer to this is that dr dt, the rate of change of the particle, referring to its distance from the origin with respect to time, is negative square root of 3. So that would be choice C.